All right, here we go. Curve sketching. So we will put together all the pieces that we've learned so far regarding our hello. Regarding our first and second derivative test, limits as x approaches infinity, everything else. And we start with this. When we look at a function, we kind of decide what does the function look like. We should start with the domain. What do we put into the function? We should identify the range, the outputs. Often there are intercepts. To find the x-intercept, what do? Set on the x-intercept, let y equal 0. And for the y-intercept, let x equal 0. Sometimes, different functions have symmetry. We won't worry about testing for symmetry. Sometimes functions have what we call asymptotes. That often happens when you get 0 in the denominator. When you want to consider intervals of increasing and decreasing, does anybody know how we find where functions are increasing and decreasing? If f prime of x is greater than 0, the function is increasing. If f prime of x is less than 0, the function is decreasing. Do you know how we determine if there's a local maximum? Where f prime changes from? Positive to negative. A min is where f prime changes from. Negative to positive. Concavity is where what? Now, if we have f double prime is greater than 0, then it's concave up. If f double prime is less than 0, it's concave down. And where f double prime changes sign, you have what we call a point of inflection. And finally, the end behavior of a function, we consider the limit as x goes to positive or negative infinity of the function. So we now have all the tools that we need to be able to get great sketches of graphs. And so we're going to do 2 in class today. We will do 1 in class tomorrow. Let's use the guidelines we've set forth to be able to find the sketch of this curve right here. Okay. We want to be able to do this guy right here. So you will not be able to sketch this graph on your test. You won't be able to use the graphing part of your calculator at all for this. This is something you have to be able to determine on your own. Okay. And so, people will kind of wonder, where do we start? Well, it's up to you. When I look at the function, I like to start with domain. Do you know the domain for a polynomial? All real numbers. Yep. So it's going to go from positive infinity to negative infinity. And the range is going to follow suit as well. Do you know the general shape of a cubic? Yeah, it's going to look something like that. So we've kind of got that piece within our mind. That's great. I like to also look at the intercepts. The intercepts are often great things to be able to find. I want to find the y-intercept, so I plug in 0 for x, and I get 0. Y is equal to 0 is the y-intercept. In order to find the x-intercept, I will set the function equal to 0. 0 equals x cubed minus 2x squared minus 3x. Some functions are very difficult to find the intercept for. This is not true for this one. We have no problem finding the intercept here. We can simply factor out an x and we get x squared minus 2x minus 3, or x times x minus 3, x plus 1. So we found that this actually has how many intercepts? 3 of them. So we have x is equal to 0, 3, and negative 1. Now, please don't sketch this, but we have had times, and it was just last year, you remember some of the good times we had together, okay, where we sketched stuff like that, and you guys said, well, how high or how low do we go with that part of the graph? Josie, do you remember asking that? Of course she does, yes. It was a joke. She kind of gave the look like, yeah, right, why would I ever ask that? Because you love math, that's why, Josie. Very good. So we want to be able to figure out those points. So it's not enough just to see the x and y intercept. I am in behavior. I'm going to find the limit of this function. If I want to find the limit as this goes to infinity, what do I factor out? Yeah, you factor out an x to the third. X cubed times, what will remain if you factor out an x cubed? 1. Then what? Minus. These will go to 0. So now that I've done that work, you can say the limit as x goes to infinity, so we're going to go to positive infinity. If you would plug in a large positive number for x, what would you get? You would get a large positive number. It would head towards infinity. So the limit as x goes infinity of the function is infinity. And then the limit as x goes towards negative infinity, if I punch in a large negative number for x, what will I get? A large negative number, so it goes to negative infinity. So again, that kind of confirms to us that it has that shape. As you remember last year, we said, oh, that's degree 3. It's positive, so it ends up and it begins down. That's what we've just confirmed there when we did that kind of work. We good? All right, so all that's the algebra, and you guys are really good at algebra. Algebra is old news for you. So let's not do the algebra anymore. Let's do the calculus. Let us show our first and second derivative tests. F prime of x is what? 3x squared minus 4x minus 3. Okay. So I'm going to set that thing equal to 0 and be able to find where it crosses the x-axis. What shape does that make? Parabola right side up or upside down? Right side up. Let's figure out where it crosses the x-axis. Anybody got the handy-dandy quadratic formula in their calculator? Type it in. If you don't have that yet, go to my YouTube video, 4 minutes and 2 seconds. I'd appreciate that. Who's got a value for me? So we have 1.87 negative 0.54. Is that correct? Very good. So what that tells me, my first derivative test, you tell me what I now know given that information. What can I now put in place here? How do I know increasing? Where f prime of x is greater than 0, that would happen from negative 0.54. Very good. Union with. Excellent. So I know my interval of increasing. Intervals of increasing. I also know my intervals of decreasing. That'll be from negative 0.54 to 1.87. Great. What else can I learn from this first derivative test? It tells me a lot about the hidden behavior of this graph that we wanted to know before, but we didn't quite understand. What else do I know? Yeah, I know the location of the x values for the local max and local min. Where does it have a local max? Why at negative 0.54? So it changes from positive to negative. Very good. So negative 0.54. So these are all intervals up here. These are all points. They are locations. So the local min will happen at 1.87. We're going to hang on just for a second here. We're not going to actually find the y values yet. We'll do that in a little bit, okay? What do I do in order to find inflection and concavity? Second derivative. So I have my first derivative. Somebody tell me the second derivative. Do you know what that shape looks like? What? It's a line. Where's it cross the x-axis? Crosses the y-axis at -4. Where's it cross the x-axis? 2/3. Very good. I can see where it's positive. I can see where it's negative. What does that tell me about the original graph? Great, I've got the second derivative test. What does that tell me? Okay, the inflection happens at 2/3. So it changes concavity at 2/3. That's going to be a point. We don't know the y value yet. We'll find that in a little bit. Concave up from 2/3 to infinity because the second derivative is positive. Very good. So I have 2/3 to infinity. And it looks like concave down then from negative infinity to positive 2/3. We all good there? A lot of times you get asymptotes if you're dealing with rational functions. In this case, it's a polynomial. It's a very nice behaving function. We don't have any asymptotic behavior, is what they say. So that's the technical term. What's that, Lexi? You said, haha. I said, asymptote. Oh, we're rolling for fun here. So I go to my graph and I type in x cubed. What do we have? I can't see it. What else we got? Minus 2x squared, minus 3x. And I'm going to go to my table and I'm going to type in negative 0.54. And it's going to give me a y value of 0.88. And I'm going to type in 1.87. I'm going to get a value of negative 6.07. And I'm going to type in 2/3, 2 divided by 3, and I get negative 2.6 approximately, negative 2.59. Okay? And now I should be able to give an excellent, excellent picture of this graph. It looks like I want to go all the way down to -6. So what I'm going to choose to do at this time is I'm going to make a graph that is 4 wide and 8 tall. 2, 4, 6, 8. 2, 4, 6, 8. 1, 2, 3, 4. Those red marks are points that I can put in place. 0, 3, -1. We looked at that originally, didn't we? But the question was, how high do we go after you cross through the x-axis? Well, your local max and local mins tell you exactly how high and how low you go. Negative 0.54, so about -1/2, and 0.88, so not quite up to +1. That's how high you go. Oh, thank you. Each one is 2, so that would have been 2. Yep. Nice job. Local minimum 1.87. So over 1.8 and down -6 approximately. So that's how low I go. And then it says I have inflection at 2/3, -2.59. So 2/3 and -2.59, about right there. That's where I change from being concave down to concave up. And if you just follow the directions that you're given, we start by increasing, then decreasing, then increasing. So 1, 2, 3. So I go increasing, decreasing, increasing. I start by going concave down, and I end by going concave up. So increasing, decreasing, concave down, now concave up, and increasing, and there's my graph. Now, I know that took a little while. We got a recorder going in 15 minutes. We were teaching, so obviously we're going to take a little bit more time there. But if we go to our window and we type in -4 and +4 for our x values, and then -8 and +8 and tick mark every 2, and we check out that graph compared to the one that we have, yeah, I'm going to say that Isaac Newton and those guys were doing pretty well, wouldn't you? Yeah. Okay. Second example for today. You tell me something that's different about this one. It's a fraction. Yep. What else? I have asymptotes. In fact, where is this undefined? So I have a vertical asymptote of x equals -2. Now, we're going to get to the horizontal one here in a second. I'm going to try to show you a connection that some of you guys will put together, some of you will not. I apologize for that, but I'm going to do my best. Let's first consider the intercepts. The y-intercept happens when what is what? When x is 0. So if I put 0 in for x, I get 0 over 2, which is 0. Great. The y-intercept is equal to 0. When you consider the x-intercept, you let the function equal 0. Now, you went through this last year. Please understand, when a fraction is equal to 0, is a fraction equal to 0 when the top is 0 or when the bottom is 0? When the top is 0. So, when is the top equal to 0? When x is 0. So, it looks like we have an x-intercept of x equals 0 as well. So, that's how you consider a fraction equal to 0. Now, I do anticipate that this is going to have a little bit different end behavior, as it is a rational function. Its domain is for all real numbers except for -2. That is what we see with the x equals -2. Let's consider the end behavior. What do we factor out of the top? An x. What do you factor out of the bottom? And you're left with and you can see that what goes away? The x's go away, and you get 3. So the limit as x goes to positive infinity, if you plugged in a large positive number in the top and a large positive number in the bottom, would you end up with a positive or negative? A positive. So the limit as x goes to positive infinity is in fact +3. If I plug in a large negative number in the top and a large negative number in the bottom, you're going to get a negative over a negative, which is going to be positive. So the limit as x approaches negative infinity is -3 or is +3 as well. So that means that as a horizontal asymptote of y is equal to 3. The end behavior in horizontal asymptotes, those are often the same pieces, especially if it's a rational function. So I'm going to make a 6x6 graph and kind of start putting some pieces in place. We have a vertical asymptote of x equals -2. We have a horizontal asymptote of y is equal to +3. I know it passes through the point 0, 0. You You must, on the test, use your first and second derivative test in order to confirm the other pieces. Let us talk about this. How do I find f prime of x? What do I have to do? Quotient rule. What's the derivative at the top? Times x plus 2 minus 1 times 3x. All over x plus 2 squared. And what I get is 3x minus 3x, or just positive 2 over x plus 2 squared. Tell me something about the bottom. Always positive. Why? It's being squared, so it's going to be positive. Tell me something about the top. It's always 2, which means it's always positive. So you have positive over a positive, which always be 6. Sorry. Thank you. So I got 6. So I always have a positive over a positive. So that means the first derivative is always positive. So therefore, the function is always increasing. The function is always increasing for all domain values. What's the one spot where it does not have a domain value? Whereas at -2, it's undefined, right? So everywhere on this side, it would be positive, and everywhere on this side, it would be positive. But you can't say that it's increasing from -infinity to positive infinity. You must exclude -2. So it's increasing from -infinity to -2, union with -2 to infinity. Nothing happens at -2. -2 isn't part of the function. When is it decreasing? Never. Does the first derivative ever change sign? So do you have a local max or local min? No. What do I have to do in order to find concavity and inflection? Consider the second derivative. What rule do I have to use to find the second derivative? Let's use the chain rule. We have 6 times x plus 2 to the -2, don't we? I mean, if you have the chance to use the chain rule, that's a good thing for us, isn't it? So you have 6u to the -2, and you have x plus 2. Derivative of 6u to the -2. That derivative is 1. So we have f double prime of x is equal to -12 over x plus 2 cubed. Is the top ever equal to 0? In fact, the top is always, is the bottom always positive? No, so we need to test. And we're going to test on either side of -2. What value would you like to plug in that's to the left of -2? If I plug in -3, -3 plus 2 is negative. Cubed would be negative, and a negative divided by a negative is positive. Now what value would you like to plug in? 0 is a great number to plug in. Plug in 0 plus 2 and cube it, we get a positive. Negative over positive is negative. So what that tells me is what? Concave up from? Concave up from -infinity to -2. Concave down from? To infinity. It changes sign at -2, but is -2 part of the original domain? Therefore, you do not have a point of inflection. So this is all the work that confirms our shape. And so you can tell we don't have a lot of data points, but we do have, in fact, these asymptotes. Is it in the top or bottom? Why? It's always increasing, and it starts concave up as well, right? Always increasing and concave up it starts. So that would mean it would have to have that shape. If we sketch that into our graph for y equals, we come up with an excellent, excellent example as well. Here's a connection for you, and then I'll let you work. Do you remember doing this last year? What do you multiply x by to get 3x? 3. Multiply the 3 through, you get 3x plus 6. Subtract, and we get negative 6. So it's a minus 6 over x plus 2. So this rational function was negative 6 over x plus 2 plus 3. So we said because it's a plus 3, it shifted up 3 units. That's my horizontal asymptote. Because you have a plus 2, it shifted to the left 2. And because there's a negative in the top, you have a vertical reflection. Instead of being in the bottom and top, you're in the top and the bottom. So this does pair with exactly those things that I know you don't forget anything from last year. So I just wanted to make sure that you saw that connection back and forth. Good. You have a nice basis for being able to try these problems.